This is AP Chemistry, Cram Study, Unit 1. In Unit 1, we're going to learn different forms of the matter, definition of an atom, atomic structures, different forms of an atom, which is called isotopes, and the energy levels of the shells and subshells, electron configuration, and periodic trend. Let's get started. So we're going to start from the definition of an atom. We learn atom, we learn atomic structure and its property because atom is the building block of all the matter in the world. Okay, so any matter in the world, the glass, rubber, plastic, wood, metal, all of these consist of the small particles called atoms. That's why we learn atom. So Dalton is the first scientist ever in the history who suggests the idea of atom. He claimed that all the matter in the world consists of small particles called atom, well, which is correct. And then he stated that, atom is indivisible, it's the smallest unit. Well, that's not actually correct because later other scientists have proved that atom consists of smaller units, which is called nucleus and electron. And nucleus consists of protons and neutrons. Okay, so protons and neutrons, the proton carries the positive charge, neutron is neutral by the name suggests. Okay, they are tightly packed around each other and then they reside in the center of an atom. And electrons move around these nucleus. Okay, and then right in between the electrons and the nucleus, it's just empty space. Nothing is there. So this is the very basic structure of an atom. When we refer to something as an atom, we're always referring to something that's neutral. Atom can never carry a positive charge or negative charge. Atom is always neutral, which means for any of the atom, it has the same number of the protons and then the same number of the electrons. So the charges get canceled out, the atom remains neutral. There are different types of atom, and then we call each of the type as element. Well, this is the periodic table of the elements. You've seen this table so many times if you've learned chemistry in high school. Each of the cubicle represents different types of elements, and let's break it down into different parts. So right in the center we have the symbol. So let's say capital letter C represent the carbon, and then on the left top corner or on top, right in the center we have an integer. 6. So this number is called atomic number, and this is actually the most important thing when it comes to an element. So atomic number of an element is like their ID card. Different elements are assigned different atomic number. If you take a look at this periodic table, you will observe that no two elements have the same atomic number. All of them have different atomic numbers. Atomic number, if any element has atomic number of 34, then it's selenium. If it has the atomic number of 3, then it's lithium. If it has atomic number of 5, it's a boron. Atomic number determines the identity. That's the most important thing when it comes to an element. And this is the same as the number of the protons. Okay, for any of the atom, the proton number is always the same as the number of electron. When it comes to proton and neutron, they have approximately the same mass and approximately the same size. They're about the same. On the other hand, electron is like very, very, very small. Electron has negligible mass, and it doesn't even occupy that much of the space compared to the protons or the neutrons. When we calculate the mass of a single atom, we just simply add up the number of the protons and then the number of the neutrons because their mass ratio is approximately 1:1. So proton plus the number of the neutron is equal to atomic mass. This means I can calculate the number of the neutrons by subtracting proton from atomic mass. So let's say for carbon, it has atomic number of 6. So it has 6 protons, and then it has atomic mass of 12.011. So 12 minus 6, that will be 6 neutrons. And since it's carbon atom, it has the same number of the electrons as the protons. So it's 6 electrons. Then what about for fluorine? For fluorine, it has atomic number of 9, so 9 protons, and it has the same number of electrons, so 9 electrons, and it has the atomic mass of 19. So 19 minus 9, that will be 10 neutrons. So remember that for each of the element, they might have the same number of the neutrons and protons, or they might have different number of neutrons and protons. But these two numbers will be approximately the same. And as the atomic number increases, the difference gets a little bit larger. Let's say, for example, xenon has atomic number of 54, so it has 54 protons. It's a pretty big number, and it will have 54 electrons, of course. And the number of the neutrons will be 131 minus 54, which is equal to 77. Now you see a big difference between the number of the protons and number of the neutrons. You will see this trend across the periodic table. But for most of the elements that we are familiar with, at the top of the periodic table, they have approximately the same number of the protons and the neutrons. Well, for example, for xenon, its atomic mass looks a little bit weird to me, 131.294. So this is not a whole number. This is not an integer. Let's say for argon, that's 40. For neon, that's approximately 20. For fluorine, that's approximately 19. But xenon has 0.294, which cannot be really rounded to a whole number. Okay, and there are some other elements like that, such as for chlorine. For chlorine, its atomic mass is 35.45, approximately 35.5. That's weird. So what does that mean? Does it mean that chlorine has 17 protons, 17 electrons, and 35.5 minus 7, so 18.5 neutron? Is that what it means? 18 and 1/2 of the neutrons? It doesn't really make sense because protons, neutrons, and electrons, they're already like the smallest unit. They are not divisible. You cannot break them down into smaller units like 1/2 the protons or 1/2 the neutrons. Okay, so why is that? Why is the reason that it has like 0.453 as an atomic mass? It's because there are different multiple isotopes for chlorine element. Okay, then what is an isotope? So isotope of the same element means they are different forms of different forms of atoms for the same element. So they have the same identity. They are like twins. So they have the same number of the protons, but different number of the neutrons. For carbon, we have carbon 12 and carbon 13. They are twins. They have exactly the same identity. They look exactly the same. But one of them is a little bit skinnier. The other one is a little bit heavier. That's the only difference. Okay, and for carbon, because it has atomic number of 6, it has 6 protons, and then 12 minus 6, which is equal to 6 neutrons and 6 electrons for carbon 12. Then what about for carbon 13? It's exactly the same. They're twins. They have the same identity, and I told you that I said the number of the proton represent the ID. So it has 6 protons as well and 6 electrons. But the number of neutron is different. So 13 minus 6, that's 7. So carbon 13 has 7 neutron. So the number of the neutron is the only difference when it comes to isotopes. And how we identify isotopes of the same element is by using this machine called a mass spectrometer. So on the mass spectrometer, we have a detector, and then different isotope will fall at different position of the detector. So if you have like 2 spots, then there are 2 isotopes. If you have like 3 spots, then there are 3 different isotopes. And mass spectrometry will generate a diagram like this. So based on this diagram, I can easily tell how many different isotopes there are. Okay, the point is, I'm interested in the average atomic mass. I mean, how did you get 35.453 as the average atomic mass of a chlorine? Okay, so when we calculate the average atomic mass of any of the element, I calculate the weighted average, not a simple average, weighted average of different isotopes of the same elements. Okay, which means for each of the isotope, they occur in different percentage or different abundance in nature. So I will have to consider its percentage in nature and then calculate the average weight. Okay, so here is an example question. The average atomic mass of naturally occurring neon is 20.18 AMU. There are 2 common isotopes, 1 is neon 20, which has a mass of 19.99 AMU. The other one is neon 22, which has the mass of 21.99 AMU. Calculate the percent abundance of each isotope. Okay, so percent abundance is actually the percentage of each of the isotope in nature. Well, there are only 2 isotopes in nature, which means when you add up the percentage abundance of these 2, you will get 100%. Okay, so when you add up these 2, you will get 100%. So if I set one of the abundance, one of the percent abundance as x, then the other abundance will be 100% minus x, or which is simply 1 minus x. Okay, and as I said, how you calculate the average atomic mass is by calculating the weighted average. So what I'm going to do is I will multiply the mass of each of the isotope by its percent abundance. Okay, so I got these 2 products, and eventually I will add them up. So I will add up these 2 products. And then that will be my average atomic mass. So 20.18 is equal to 19.99x plus 21.99 multiplied by 1 minus x. So 20.18 is equal to negative 2x plus 21.99. 2x is equal to 1.81, x is equal to 0.905. This means the percentage abundance of neon 20 is equal to 90.5%, and the percent abundance of the second isotope neon 22 is 9.5%. So that's it. So this is how you calculate the average atomic mass of an element based on their percent abundance and the atomic mass of each of the isotope. Okay, so here are like different types of the questions. This is actually the type of questions that you see often in AP chemistry exam. You are given this diagram and then you are asked to calculate the average atomic mass or estimated or identify the element based on the estimated average atomic mass. Okay, so I'm going to teach you like simple ways to do it. So the relative abundance, it's not given in the form of the percentage, right? It's given in the form of the integer 961. It just represents the ratio. The ratio of the isotope 70, 72, 74 is 9 to 6 to 1. So how I do this type of question is by multiplying the mass of each of the isotope by the percent of the corresponding isotope. So it will be 9 divided by 9 plus 6 plus 1 plus 72 multiplied by 6 over 9 plus 6 plus 1. So this represents the percent of the 72 isotope in the whole sample, plus 74 multiplied by 1 over 9 plus 6 plus 1. Okay, well, if you have a calculator, you can just easily come up with an answer. The thing is, in MCQ questions, a lot of times you're not allowed to use a calculator. You're just allowed to estimate it. Okay, here is my method to estimate it. So I'm going to take a look at the highest picks. So 70 is the highest pick, 72 is the next highest pick, and then the ratio is 3 to 2. The ratio of these 2 picks is 3 to 2. Okay, so when you take the average, the weighted average of these 2 picks, you will get a number that is even slightly less than 71, because 70 and 72 has average of 71, but you have more of the 70, so your average will be actually less than 71. Okay, and then because you add them up together, now their weight will be 15. 9 plus 6, that will be 15. So this pick, you can get rid of these 2 picks. You will have a new pick, which is slightly less than 71, and then it has the height of 15. And now you're going to take the average of these 2. Again, it's weighted average. And because the taller pick, the pink one, is so much more taller, it's 15 to 1. So this pick is actually negligible. So 71, well, when you take the average of 74, it will increase a little bit, but I will still it will be still like somewhere like around 71. So I will say it's approximately 71, like slightly less than 71. Okay, what about the next one? So it has only 2 peaks, which means it has only 2 isotopes. Okay, now this will be easier. And then the peak with 10, atomic mass of 10, has the height of 25, and then the other one with the atomic mass of 11 has the height of 100. So that will be 10 multiplied by 25 over 25 plus 100, plus 11 multiplied by 100 over 25 plus 100. So that will be 10 multiplied by 1 over 5 plus 11 multiplied by 4 over 5. So that will be 10.8 AMU. So this will be the average atomic mass for this mass spectroscopy. Okay, next, here's another question. Based on the mass spectrum of a pure element represented above, the average atomic mass of the element is closest to which of the following? Well, this is the type of question that you need to estimate rather than using a calculator to actually come up with the exact number of the atomic mass. So I have 2 peaks, so 2 isotopes. One is 185, the other one is 187, and then the relative abundance is 40% and 60%. Okay, well, if you take the average of both, if both of them were like 50-50, then you will get 186. But now you have more of the 187 than 185, which means the weighted average will be greater than 186, slightly greater than 186. So it will be 186.3. Next, let's talk about different forms of the matter. We can classify all the matter in the world depending on their forms. Elements consist of the same type of the atoms only. Metals such as copper, zinc, silver, they just exist in the form of one single atom. So just by copper, Cu, it represents the exact copper. And then the silver, it can be just represented in terms of Ag. There are some other substances that can be represented as the multiple atoms of the same element, such as the oxygen gas, O2. So oxygen gas consists of 2 oxygen atoms combined together, or hydrogen gas, H2, or nitrogen gas, N2, or ozone, O3. Okay, so oxygen gas and ozone, these are 2 different substances, but both of them can be written in terms of the same element, of one single element, oxygen. So these are considered elements. They can be written in terms of the same type of the element, the same type of the atom. Then what is a compound? Compound is a substance that can be written in terms of 2 or more than 2 different types of atoms, such as when copper reacts with oxygen, it forms copper oxide. Let's say water, it's when hydrogen and oxygen react, so H2O. So hydrogen, oxygen, these are 2 different types of compounds. Ethanol, the alcohol, it consists of carbon, hydrogen, oxygen, 3 different types of atoms. So these are what we call by the compounds. And both of them fall in the category of pure substance. When you mix multiple pure substance, then you get the mixture. When you mix 2 or more different types of pure substance, then you get mixture. Well, so you will get a bunch of different types of mixture. You can just mix 2 different types of elements. So let's say I mix copper and silver to make some jewelry. If I mix oxygen and then the ozone, then it's still the mixture, even though it consists of the same atom, oxygen, but it's still considered mixture. Because oxygen and ozone, they actually can be written as 2 different types of the chemical formula. So they're 2 separate substances. When you mix the compounds together, let's say you are going to mix the water and then the alcohol. So you have CH3, CH2OH, and then the water mixed together. This is still the mixture. So you can combine them like in a way like whatever you want. You can combine elements with compounds. You can just mix the compounds with compounds. You can mix elements with elements, and then you will get mixture. And in the mixture, you have two different categories as well. One is homogeneous, the other one is heterogeneous. Well, based on the name homo, we know that this is, the homo means same, right? So it means the mixture is, these two different pure substances is mixed evenly, so you can't tell the difference between them. So one of the best example for homogeneous mixture will be saline water. So in a beaker of saline water, you can't really tell which part is salt, which part is water. They're thoroughly mixed with each other, unless there is salt undissolved at the bottom of the solution. But let's assume that all the salt has been dissolved. You can't really tell the difference. And when you taste this portion of the saline water and then this portion of the saline water, they taste exactly the same, and then they look exactly the same. You can't tell the difference. This is what we call by homogeneous. When you mix the alcohol and water thoroughly, you will still get a homogeneous mixture. You can't tell the difference which part is water, which part is alcohol. And the other one is heterogeneous. So heterogeneous is something that's not mixed evenly. Let's say salad. So salad has the dressing on top of it. It has a cheese, it has olive oil, it has leaves, everything. Well, even though we mix it thoroughly, but you can still tell like the leaves apart from the cheese, apart from the olive oil, you can tell them apart. So this heterogeneous, so most of the mixtures in real world situation is actually heterogeneous, such as pizza. So on pizza, you have dough at the bottom, you have sauce, and then you have cheese, and then you have like toppings. Okay, so this is heterogeneous mixture. Or let's say when you have pasta, and then the pasta mixed with, let's say, the cream and then the sauce and then the toppings, this is also heterogeneous mixture. This is an example of the homogeneous mixture. They are mixed evenly. In this heterogeneous mixture, you can see like a cluster of the compounds and then a cluster of the elements. So they're not mixed thoroughly or evenly. So this is what we call by heterogeneous mixture. Then how do we separate different mixtures from each other? If something is insoluble, then you can actually just separate it by using a funnel with a filter paper. You are going to put a beaker at the bottom, and then by using a funnel and then the filter paper, you can just run the mixture, and then eventually you will have whatever that's insoluble left in the filter paper and funnel. You will have the soluble mixture at the bottom. What if something is soluble? So such as sodium chloride, like table salt dissolved in water. You can just boil it. We call it by evaporation. By evaporation, you're just removing the water, and then you will have the solid table salt left. Or you can do distillation. So distillation is used to separate two liquids, such as alcohol and water. So alcohol and water have different boiling point. Water boils at 100 Celsius degree. Alcohol boils at approximately 78 Celsius degree. You're going to set the temperature around 80, slightly higher than the temperature of the alcohol. Then eventually, all the alcohol will be evaporated, and then the leftover is the water. And you're going to collect the vapor, evaporated vapor. You're going to collect it and then cool it down. And eventually, you can collect the liquid form of alcohol. Barium in aqueous reacts with sulfate to produce barium sulfate in solid, which forms precipitate. A student obtains 10 gram sample of the white powder labeled barium chloride. After completely dissolving the powder in 50 milliliters of the distilled water, the student adds excess sodium sulfate, which causes a precipitate of the barium sulfate to form. Okay, the student filters the barium sulfate, rinse it, and dries it until the mass is constant. Which of the following scientific questions could best be answered based on the result of the experiment? First off, I know C and D are not the right answer. I can just immediately cross them out because it's asking about the solubility, and this question has nothing to do with solubility. There are couples of the keywords that you need to pay attention to. It says excess sodium sulfate. So the limited agent in this question is the barium is the barium ions. You can only explore if the limited agent is pure or not pure, not the excess agent. So it's not going to be A, the answer will be B. How we can determine if barium chloride is pure or not pure? Based on the mass of the barium chloride, you can calculate mass of the barium. This is theoretical. This is theoretically the amount of the barium that you expect to have in 10 grams of the barium chloride. And then this is what you actually get. This is experimental. The experimental value will, of course, be less than or equal to the theoretical value. If it's the same, then it is pure. If mass of the experimental value is less than the mass of the theoretical value, then it means barium chloride used for the experiment is not pure. How do we actually measure the matter? So chemistry is a quantitative science, which means when you do a chemical reaction, you always want to know how much amount you are using or how much of the products you are going to get. You can measure the matter by volume or by mass. By volume, you're going to measure it using milliliters or liters. By mass, you're going to use grams most of the times in chemistry. Or you can actually count the number of the particles. We just learned that matter consists of small particles called atom, and each of the atom carries exactly the same mass, and then they have the same size, they have the same properties. So we can actually count the number of the particles. The thing is, this is actually almost impossible because the atom size is so small. It's even smaller than a grain of salt. It's barely possible for us to count the numbers exactly. Okay, so what we use instead is we measure the matter by mole. So mole is a unit that we use often in chemistry. That's just like a dozen. So we know that a dozen always means 12. A dozen of eggs means 12 eggs. So if I want to buy 24 eggs, it's just 2 dozens of eggs. Then like 3 dozens of eggs is 36 eggs. We use mole as a packet to represent like a certain number of the particles. And this number is Avogadro's number. So Na, Avogadro's number, is equal to 6.022 times 10 to the power of 23. So you have this many particles for 1 mole. Okay, so number of moles is represented in terms of the small letter n. So n is, when you multiply this number by the Avogadro's number, you will always get the number of the particles. So 1 mole of any of the particle is equal to 6.022 times 10 to the power 23. And when I said particles, it can be atoms, it can be ions, it can be molecules. When you are given the number of the mole, how you convert it to the number of the particles is by multiplying it by the Avogadro's number. Then how do you convert it between the number of the particles and then the mass of this sample? We're going to multiply something called the molar mass. The molar mass is mass of any substance. This substance can be molecule, it can be ions, it can be atoms. Mass of any substance for 1 mole. And how we find the molar mass is when we take a look at the periodic table, the atomic mass. The atomic mass of any of the atom represent its molar mass. So let's say for boron, its molar mass will be 10.81 grams per mole. Let's say for nitrogen, its molar mass will be 14.01 grams per mole. This is the molar mass of all of the atoms. And if you have, let's say, molecules such as H2O, then you're simply going to add up their molar mass by the ratio. So you have 2 of the hydrogen, 2.1008, and then you're going to add the molar mass of the oxygen, 16. So eventually you will get 18.016 grams per mole for the H2O, for water. Okay, so when you multiply the number of the moles by the molar mass, the units get canceled out. The units of the mole get canceled out, and then you will get the mass. Okay, so you will have to memorize this triangle, and you have to be very, very familiar with the conversion, the mole conversion. And if you're given the mass, then if you want to get number of the particles, then you'll have to do a two-step calculation. If you're given the number of the particles and you want to know the mass, then you have to do the two-step calculation as well. So two formulas to remember. Mass is equal to number of moles multiplied by molar mass, and then number of the particles is equal to number of the moles multiplied by the Avogadro's number. Okay, so here's an example question. What is the number of the moles in 5 grams of calcium chloride? You are given the mass of the sample. It's 5.0 grams of calcium. Mass is equal to number of moles multiplied by the molar mass. Then the number of the moles N will be equal to mass divided by molar mass, or 5.0 grams of the calcium chloride divided by its molar mass. Then what is the molar mass? On the periodic table, I will have to find the molar mass of the calcium and chloride. So I have calcium here and then the chloride here. Then calcium chloride will have the molar mass of 40.08 plus 2 times 35.45, which is equal to 110.98 grams per mole. Okay, so I'm going to divide the mass of the calcium chloride by this number. The units get canceled out, then you will be left with the unit of the mole. And the answer will be 0.0451 mole of the calcium chloride. And next, how many molecules are present in this sample? Okay, so molecules, calcium chloride, it behaves as one single unit. This is the one molecule. The number of the molecules of the calcium chloride will be equal to the number of moles multiplied by Avogadro's number, which is equal to 2.71 multiplied by 10 to the power of 22 calcium chloride particles or molecules. 1 calcium chloride particles, you have 1 calcium and then 2 chlorine atoms, which means in total you have 3 atoms in 1 calcium chloride molecules. Okay, so the number of the atoms will be equal to number of the molecules multiplied by 3 atoms per molecule. So this will be equal to 8.14 multiplied by 10 to the power of 22 atoms. The next question, a sample of calcium carbonate contains 4.86 moles, so it's given the number of moles. What is the mass in grams of this sample? So the number of the mole is given. It's asking me to find the mass. Okay, again, I'm going to use the formula. Mass is equal to the number of moles multiplied by the molar mass. Then it will be 4.86 mole multiplied by the molar mass. Okay, again, I will have to find calcium, carbon, and oxygen. So CaCO3, 2 minus. Okay, so carbon has the mass of 40.08. Carbon is 12.01. Oxygen is 16. So it will be 40.08 plus 12.01 plus 3 times 16, 100.09 grams per mole. Okay, so I'm going to multiply the number of moles by that. This is equal to 486.44 grams. Okay, and what is the mass of the carbonate ions present? So for 1 mole of the calcium carbonate, you have 1 mole of the carbonate ions, right? Okay, which means what is the molar mass of the calcium carbonate? 100.0 0.09. So which means for 100.09 grams of the calcium carbonate, because these two actually represent the same amount of the calcium carbonate. 1 mole, or you can like measure in mass, then it's 100.09 grams. This is exactly the same amount. Then what about for the carbonate? Okay, so the carbonate, the molar mass of the carbonate will be this part only, which is 60.01. So 1 mole of the carbonate is equal to 60.01 grams of the carbonate ions. This ratio is the same as this ratio. This is how I converted the mole ratio into the mass ratio. 486.44 grams of the calcium carbonate multiplied by 60.01 grams of the carbonate in 100.09 grams of the calcium carbonate, 291.65 grams of the carbonate ion. So molecular formula represents the smallest unit of a molecule. For example, C6H12O6 is glucose, 6 to 12 to 6. This is not the smallest whole number ratio. So if you converted it to the smallest whole number ratio, then it will be 1 to 2 to 1. So I just plug in all the atoms, and it will be carbon 1, hydrogen 2, and oxygen 1. C2H4, its empirical formula will be CH2, because the ratio of 2 to 4 can be simplified to 1 to 2. Or let's say C2H6, ethane, its empirical formula will be CH3. Remember that only the molecular formula is what actually represents a molecule. And then if a molecule wanna maintain the property, then it has to be in the form of the molecular formula. Then why do we need to know empirical formula? What is it used for? So empirical formula is especially useful when we're trying to figure out the chemical formula of an unknown substance. Let's say mass percentage of an unknown substance is 40% carbon, the 6.67% of hydrogen, 53.3% of oxygen. Well, sometimes the exact mass is given, sometimes it's the mass percentage. That's exactly the same. How we solve these type of problem is exactly the same. So what I'm going to do is I'm just going to take the number and then divide these number by the molar mass of each of the element. 40 divided by the molar mass of carbon, which is 12.01, then it will be 3.33. This is the number of the carbon, okay? And next, for the hydrogen, it will be 6.67 divided by the molar mass of the hydrogen, which is 1.008. Then you get 6.62 hydrogen. And next, 53.33 divided by the molar mass of the oxygen, 16. 3.33 oxygen. And now I'm going to calculate the whole number ratio of these numbers. 3.33 carbon to 6.62 hydrogen to 3.33 oxygen, okay? Well, I'm going to divide each number by 3.33 because I have two of the 3.33. Then it will be 1 carbon to 1.99 hydrogen to 1 oxygen. Well, not 1.99 hydrogen is approximately just 2. It can be round up to 2. So it will be 1 carbon to 2 hydrogen to 1 oxygen, which means the empirical formula for this substance will be carbon, hydrogen 2, and oxygen, CH2O. This is one of the most important methods we use to figure out the identity of an unknown substance when you are given only the mass percent of different elements. The next question is, then how do you calculate the molecular formula? Okay, first off, you need to have empirical formula. That's the very first step. And then you need to know the molar mass of this sample or this substance. And then you can figure out the molecular formula. Okay, so let's say a compound with an empirical formula of CH2, the empirical formula is already given, we don't have to do any more calculation, has molar mass of 70 grams per mole. First off, what I'm going to do is calculate the molar mass of the empirical formula CH2. 12 plus 2 times 1, which is 14 grams per mole. Okay, and then I'm gonna divide the molar mass of the molecular formula by the molar mass of the empirical formula. 70 divided by 14, which is 5. So 5 will be the formula units. So I'm gonna multiply this 5 to the empirical formula. So for the molecular formula, I will get C5H10. So this is the molecular formula. Next, 42 grams of subsample of a compound containing carbon and hydrogen only was analyzed. The results show that the sample contains 36 grams of the carbon and 6 grams of the hydrogen. Which of the following questions about the compound can be answered using the result of the analysis? Okay, so this time you are given the mass of the exact mass of the carbon and exact mass of the hydrogen. Well, okay, so how you solve this type of question is exactly the same. You are gonna divide the mass of each of the compound by its molar mass. So that will be 3 carbon and 6 grams of the hydrogen divided by 1, that will be 6 hydrogen. So 3 carbon to 6 hydrogen, the ratio is 1 to 2. So I will get the empirical formula of CH2. Remember that this is empirical formula. And then because we're not given the molar mass, so there is no way for me to figure out the molecular formula yet. Okay, so A, what was the volume of the sample? Well, there is no way for me to figure this out. B, what is the molar mass? Again, this is not given. I can't figure it out based on the given information. And C, what is the chemical stability? You will have to do a series of chemical reaction to see if it reacts well or not. So not C. The only answer will be D. What is the empirical formula of the compound? And then you already figured it out, which is CH2. A student measures the mass of a sample of a metallic element M. Then the student heats the sample in air, where it completely reacts to form the compound MO. The student measures the mass of the compound that was formed. Which of the following question can be answered from the result of the experiment? Okay, so this is a reaction between the metal M and then the oxygen O2, and then they form MO. Based on this, okay, first off, you are given the mass of the sample, and then you are going to measure the mass of the compound again. So you have the mass of the M, mass of the MO. Okay. So based on this, which information can be answered? A, what is the density of M? So density is equal to mass divided by volume. And you're not given the volume of the element M. And there's nowhere for me to figure this out, so it's not A. And B, what is the molar mass of M? Okay, well, for the molar mass is equal to mass divided by the number of the moles. Okay, then I will have to figure out the number of the moles based on these two information. Okay, the thing is, based on these two data, I can just subtract the mass of the metal M in the compound. Then I will get the mass of the oxygen. And since it has the chemical formula of MO, which means the ratio of the number of the moles of the metal M and the number of moles of oxygen is equal to each other. Number of moles of the oxygen. And this is the same as the number of the moles of the metal M, which is mass divided by molar mass M. So you will be able to use this information to figure out the number of moles of the metal M, and then because you're given the mass of M, you can figure out the molar mass of M. So B is the right answer. The next question. A jar labeled sodium chloride contains a powder. The table above contains information determined by analyzing a sample of the powder in the laboratory. What information in a table is the most helpful in determining whether the powder is pure sodium chloride? Okay, so mass percent, density, and color. Okay, so just by the mass, there is no way for me to figure out if this is sodium chloride or something else, because for all different types of the matter, you can have 27.3 grams of all the matter in the world, so it's not mass for sure. Density is calculated by mass divided by volume. The thing is, different substances might have the same density, so it's not something specific or unique to a substance. So that's not density. And color, of course, not. Like sugar is also a white powder. You can't really tell it from the color or the density. So it should be only the mass percent of sodium. A student obtains a mixture of the chlorides of two unknown metals, X and Z. The percent by mass of X and then the percent mass of Z in the mixture is known. Okay, the percent by mass of X, the percent mass of Z. Which of the following additional information is most helpful in calculating the mole percent of XCl and ZCl in the mixture? And 8, the number of the isotopes of chlorine. Well, when we deal with the mole conversion, the conversion between the mass, molar mass, and then the mass, we use the average atomic mass. So the number of the isotopes doesn't really matter when it comes to the mole conversion. And B is the molar mass of X and Z, and C is the density, mass divided by volume. Volume has nothing to do with this question. It's conversion between the mass, the number of moles, and then the molar mass. So it's not C either. And D, the percent by mass of C in the mixture. So this is the mixture of XCl and then the ZCl. So it actually means that in this mixture, you have 3 elements, X and Z and Cl. This means when you know the mass percent of X and mass percent of Z, the mass percent of chlorine will be pretty obvious. It will be 100% the mass percent of X and Z. So this is very similar to how we calculate the empirical formula. You are given the mass percent, and then you're going to divide the mass percent by its molar mass, and then you're comparing these values of different elements. You're comparing this ratio of X and Z and Cl, and then you can figure out their mole percent. Okay, which means now what I need is molar mass of each of the compounds X and Z. So the answer is B. The next is atomic structure. Well, we already talked about the very basic atomic structure, which has the protons and neutrons in the center as nucleus, and then you have electrons surrounding it. So that was a oversimplified structure of an atom. And now let's dive deep into the actual detailed structure. Okay, so again, it consists of the nucleus, and electrons, and nucleus is right in the center, and then it consists of protons and neutrons. Proton carries the positive charge, neutron is neutral, and the electron carries the negative charge. The thing is, a lot of times we think or we believe that electrons are just moving around the nucleus on one single orbital, which is actually not correct. So electrons move around the nucleus in certain shells or in certain orbitals only. Okay, so for example, electrons can move on this shell, it can move on the second shell, it can move on the third shell. But electrons cannot reside in between the cell. It cannot be here or here or here. It has to be on this specific shell. Okay. And then for the specific shells, we call them energy levels. So from the innermost shell, we call it n equals 1. And then the next innermost one, we call it n equals 2. The next innermost one, we call it n equals 3. And then the outermost one, we call it the valence shell. For the outermost, we call it valence shell. So for the electrons that reside on the outermost shell, we call it valence electrons. So all of these atoms on n equals 4 are called valence shell electrons, or just valence electrons. Okay, the thing is, what's really interesting is within each of the shell, there are subshells. There are sub-energy levels. Okay, and then the sub-energy levels are S, P, D, F, and then the energy increases from S to F. So F is the highest highest sublevel, and then S is the lowest energy sublevel. And for n equals 1, we only have S shell. For n equals 2, we can have S and P subshells. For n equals 3, we have SPD, 3 subshells. For n equals 4, we can have SPDF. And starting from n equals 4, n equals 5, n equals 6, all of those have SPDF, 4 different sublevels. Okay. And based on this diagram, you can tell that as the number of the subshell increases, the number of the electrons in each of the shell also increases, and it's not proportional. For S, you can fit in 2 electrons, and then it's the same for the second shell. For P, you can fit in 6 electrons. For D, you can fit in 10 electrons in total, and then for F, you can fit in 14 electrons in total. Okay, so these can be actually very, very confusing. So here is a brief review of shell, subshell, and orbital. Again, the shell, what we also call by the principal quantum number, we represent it as n equals 1, 2, 3, it goes on. And then the innermost shell is n equals 1. The next one is n equals 2. The next one is n equals 3. And then for the subshell, it's S, P, D, F. So there are different subshells on each of the shell. As I said, on n equals 1, you have only S subshell. On n equals 2, we have S and P. On n equals 3, we have S, P, D. Starting from n equals 4, we have S, P, D, F. In each of the subshell, we can fit in multiple electrons. Okay, remember that S, P, D, they have different energy levels. So S is lower than P, P is lower than D. But within each of the subshell, when you plug in multiple electrons, they are on the same energy level, and then we call this orbitals. So for S, you can fit in 2 electrons, which means there is only 1 cubicle or 1 orbital. For P, you can plug in 6 electrons, which means there are 3 orbitals. And these 3 orbitals are just like the rooms in a hotel. So there are like 3 rooms on one single level, and then you can fit in 2 people in each of the rooms. Okay. So remember that these 3 orbitals in P, they are always on the same energy level. The orbitals are always on the same energy level, and then shell and subshell will be on different energy levels. Next is electron configuration. So for any of the atom, you have to fill in the electrons in these energy levels and energy sublevels. Well, there are certain rules when you fill them in. You cannot just randomly plug in the electrons in any of the vacant orbitals. No, you can't. There are strict rules for that. The rule of thumb is you always have to fill in from the lowest energy level. So you will have to fill the 1s in full, and then you can fill in 2s. And then when 2s is full, and then you can next plug it in 2p. And then when 2p is full, and then you can plug in the electrons in 3s. Okay, and then how do I know this? How do I know the order of this? Okay, then you're going to use this diagonal diagram. So for this diagonal diagram, you are going to list the energy subshells. So you're going to put the energy levels on the column, n equals 1, n equals 2, n equals 3, n equals 4, and then it goes on. On the row, you are going to put the sublevels of S, P, D, F. Okay, and then you're going to use this diagonal to go from the right top corner to the left bottom corner. And you're going to follow the order of this diagonal. So after 2s, 2p, and 3s, 3p, it's not 3d, even though 3d is on the same energy level as 3s and 3p. But because you're following the diagonal, you're actually going to 4s. Okay, so 3d is the highest out of the energy level of 3, and 4s is the lowest out of the energy level 4. And there is a slight overlap, and 4s is actually at a slightly lower energy level compared to 3d. So that's why you fill in the 4s first. Okay, this is the first rule you need to follow. So here's an example. Let's try to draw the electron configuration on this energy diagram for nitrogen. So nitrogen has atomic number of 7. So it has 7 protons and 7 electrons. Okay, so again, I will have to fit in the lowest energy level first. So I have to fit in the 1s orbital. So s orbital, s subshell has only 1 orbital, which means 2 electrons. And for 2 electrons in 1 orbital, they have to be paired, which means one electron will have a spin pointing up, the other one has a spin pointing down. So the spin number actually represents the exact way an electron moves around the orbital. And then in one orbital, 2 electrons must have 2 different spins. Okay, and then it will be 2s, and then again I'm gonna plug in 2 electrons in the orbital of 2s. And next is 2p. There are 3 orbitals. Okay, so I cannot plug in 2 electrons in one orbital and then another electron in the second orbital. No, this is not correct. So the second rule is you will always have to fill all the orbital on the same subshell, and then you start to pair them, which means you will have to fill in all the 3 orbitals, and then you can start plugging in more electrons in the orbitals. Okay, for nitrogen, I have 7 electrons only. So I have 1, 2, 3, 4, 5, 6, 7. So that's it. Okay, can I plug in the electrons with a downward spin? Yes. So for this part, you can replace it with downward, downward, downward. But remember that all of the 3 orbitals must have the same spin. So if you're going to draw something like downward, upward, downward, this is not correct. But all of them upward or all of them downward is fine. Next, here's another example. Let's try to draw the electron configuration of magnesium. Okay, so magnesium has the atomic number of 12, which means it has 12 protons and 12 electrons. Okay, again, starting from the lowest energy level, 1s, it's up and down, and then 2s, up and down, and 2p, it will be up, 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 down, 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 okay? And I have 1 up and 1 down. So that's it for magnesium. Okay, so this is how you fill in the energy level diagram, and then how I actually write the electron configuration will be, for nitrogen, it will be 1s2, which means in 1s orbital, I'm going to plug in 2 electrons. And then next, 2s2. Again, it means in 2s orbital, I plug in 2 electrons. And then 2p3, which means I'm plugging 3 electrons in 2p orbitals. Okay, then what about for magnesium? For magnesium, it will be 1s2, 2s2, 2p6, and then the last 3s2. Okay, or sometimes I can write this electron configuration with regard to the noble gas. Okay, so let's say for magnesium, it's in n equals 3. It's on the 3rd energy level. Okay, then let's take a look at the noble gas on n equals 2, which is neon. Okay, then I can use neon to write an abbreviated form of the electron configuration, which is bracket neon. Okay, so bracket neon represents the electron configuration of neon, which is 1s2, 2s2, and 2p6. So I just need to start from here. So it's bracket neon and then 3s2. So this is an abbreviated form of the electron configuration, and both of them are completely correct. Both are correct. Okay, next, why don't we try to draw the electron configuration of calcium 2+. Okay, remember that this is not atom anymore. This is ion. Okay, so calcium has 20 protons, right? So calcium atom has 20 protons. But then now, okay, so it's supposed to have 20 electrons if it's an atom. But now it is an ion which carries 2+ charge, which means it has lost 2 electrons. So now it has only 18 electrons. So how you calculate the charge of an ion will be the charge of the proton plus the charge of the electron. Okay, so it's positive 2. So positive 2 means it has 18 electrons only. Okay, so how I fit in 18 electrons will be, again, starting from 1s orbital up and down, 2s up and down, 2p up, 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 down, 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 and then 3s up and down, 3p up, 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 down, down, down. Okay, so how many electrons do we have for now? I have 2, 2, 6, 2, 6. So that is 8 plus 12, which is 20 electrons in total. Sorry, so how many electrons do we have for now? We have 6 electrons, 6 electrons, and 6 electrons. So we have 18 electrons for now. So that's it. Okay, we're going to stop here. So how I write the electron configuration of calcium 2 plus ion will be 1s2, 2s2, 2p6, 3s2, and 3p6. Or I can just use the abbreviated form. So calcium is on n equals 4. So I'm going to find a noble gas in n equals 3, which is argon. Okay, so I can simply use bracket argon to represent the electron configuration of calcium 2 plus ion. Remember that this is an ion, that's why it has the same electron configuration as the noble gas argon. Okay, let's try it one more time. Then what about for what about boron? Boron. Okay, so boron has the atomic mass of 5, so it has 5 protons and 5 electrons. So in the 1s, I'm going to plug in up and down 2 electrons, 2s up, down, 2p, it will be just up. So electron configuration of boron will be 1s2, 2s2, and 2p1. If I use the noble gas abbreviation, and boron is in n equals 2, so I need to find a noble gas in n equals 1, which is helium. So it will be bracket helium and then 2s2, 2p1. How many unpaired electrons are in the atom represented by the electron configuration above? Remember that in each of the orbital, if there is only one single electron, then we call this unpaired. And if there are up and down, then we call this paired electrons in each of the orbital. Okay, so for 1s2, 2s2, 2p6, 3s2, 3p6, all of the orbitals are full because in s subshell there is only one orbital, which means you can plug in a maximum of 2 electrons. In each of the p shell, it has 3 orbitals, which means we can plug in a maximum of 6 electrons. So for this one, all of the s subshells and p subshells are full, which means there is no unpaired electrons. It will be 0. 1s2, 2s2, 2p6, 3s2, and then 3p6. So as shown in this electron configuration diagram, there is no unpaired electrons. The answer is 0. Next, which of the following represent the electron configuration of an oxygen atom in the ground state? Okay, so the ground state means it's not excited. So what I mean by the ground state or the excited state is, so what we draw up until now is the electron configuration of the ground state or the most basic state. But when an atom is excited, well, usually it's excited by absorption of the energy such as a light or heat. Then the electrons get very, very excited. Then it can jump to a higher energy level. So this is represented using the Bohr model on the hydrogen spectrum. So electrons can jump back and forth, but when the electrons jump up, then it will have to absorb energy. When electrons jump down, it will have to release energy. So when it releases or absorb energy, it's usually in the form of the light or heat. Okay, and for the oxygen, so first off, oxygen has the atomic number of 8, which means oxygen has 8 protons and then 8 electrons. Okay, so 1, 2, 3, 4, 5, 6. So I know immediately A is not correct because it has only 8 electrons. Because A, it has only 6 electrons, and for B, it has only 7 electrons. So the answer is either C or D. So in C or D, in C and D, both of them have 8 valence electrons. In C and D, it has both. In C and D, both have 8 electrons. The thing is, in C, it has 1, 2, 3, up, and then down. On the other hand, D has up, down, or up, and down. Okay, remember that we always have to fill all the orbitals first, and then we can start to fill for the electrons and the orbitals to form the paired electrons. So D is not correct. C is the right answer because the last orbital of 2p is vacant, then you cannot form this paired electrons. The next is photoelectron spectroscopy. So this is a very useful method that can be used to identify the identity of an element. Usually it shows the electron distribution and energy on each of the subshells. So usually on the x-axis we will have binding energy, which is the amount of energy required to remove an electron from a certain subshell. Okay, and then different subshells have different energies as we just stated. So higher the energy level, the more energy, and then the lower the energy level, the lower energy. Okay. If we're trying to remove the electron from a higher energy level, then more energy will then. If you're trying to remove the electron from a higher energy level, less amount of energy is required. This is because higher energy actually means it's at a higher potential energy or it's unstable. On the other hand, closer to the nucleus means that the energy level is low or it's very stable. So if you want to get rid of the electrons in this very stable subshell, it's going to take a lot of energy. So a greater binding energy means that it's closer to the nucleus. The left side is close to the nucleus, and then the right side is close to the valence shell. Remember, the energy on each of the subshell is the same. Okay, so if you want to remove both of the electrons in, let's say, 2s, then it will take the same amount of energy for both of the electrons. Okay, then what does the peak represent? So the peak represents the amount of energy required to remove the electrons in that subshell. And then the height of the peak represents the relative number of the electrons. So the more electrons you remove from the certain subshell, the higher the peak. So from the left side, okay, the leftmost peak has the highest binding energy, which means this is the innermost subshell of 1s. And 1s, and then the next peak means it's 2s. Okay, to fill in the electrons in 2s, you have to fill the 1s in full. This means 1s peak has 2 electrons, so this is 1s2. And then the next peak has the same height as 1s, which means this is 2s2. And then the next peak right next to 2s. Okay, so right above 2s, we have the energy sublevel of 2p, but the height of the peak is only 1/2 of the 2s2, which means there's only 1/2 of the electrons in 2p orbitals, which means there is only 1 electron in the whole 2p subshell. This represents the photoelectron spectroscopy of a boron with 1s2, 2s2, 2p with 3 separate peaks because there are 3 sub-energy levels. Then what about for sodium? Okay, so sodium is in n equals 3. So if I try to write its electron configuration, that is 1s2, 2s2, 2p6, and then 3s1. And let's see if this diagram matches or fits the electron configuration. Okay, so from the leftmost, 104 kilojoules, 104 megajoules. So this corresponds to the innermost sublevel of 1s2. And then next 6.84, it corresponds to the next next innermost energy subshell of 2s2. And then this highest peak, which has the 3 times the height of these 2 peaks, represent 2p6 because there are 6 electrons. So the peak is 3 times higher than the peak that's for 2 electrons. And then the next will be 3s. And because there is only 1 electron, so the height of the peak is only 1/2 of the 2s and 1s2. Okay, so here's the question. The photoelectron spectrum for the element boron is represented above. Which of the following best explains how the spectrum is consistent with the electron shell model of the atom? Okay, A, the spectrum shows an odd number of electrons. B, the spectrum shows a single electron in 2p subshell. C, spectrum shows equal number of electrons in the first and second electron shells. D, spectrum shows 3 electrons with the same binding energy in the second electron shell. Well, let's try to analyze this photoelectron spectroscopy diagram first. So from the left to the right, the binding energy gradually decreases, which means the left is close to the nucleus, it's the innermost shell, so it will be 1s2. Next peak will be 2s2, next will be 2p. And because the height of the rightmost peak is only 1/2 of the other 2 peaks, it will be 2p1. So it has the total number of electrons will be 2 plus 2 plus 1, which is 5. So A is actually correct. And B, the spectrum shows a single electron in 2p. This is correct too. There is only 1 electron. C, spectrum shows equal number of electrons in the first and second electron shell. Remember, the electron shell refers to n equals 1 and n equals 2. So 1s subshell is in first electron shell, and 2s and 2p are in second electron shells. So there are only 2 electrons in the first shell, but 3 electrons in the second shell. So C is actually not correct. D, the spectrum shows 3 electrons with the same binding energy in the second electron shell. In the second electron shell, 2s and 2p represent 2 separate binding energies. So D is not correct. Then out of A and B, which one is the answer? Actually, both are correct, but which one is the explanation for the spectrum that's consistent with an electron shell model? Okay, so the odd number of electrons doesn't really tell us anything about the shell model. So A is not the right answer, it's B. So B tells us about the shell, like n equals 1, n equals 2, and then the subshells. And next, this is the last subtopic in Unit 1, periodic trend. So there are 4 categories that you are going to take a look at for a periodic trend. One is atomic radius, or just the size of an atom. And then the second is ionization energy. And then the third is electron affinity. And then the last one is electronegativity. So there are 4 categories. So we're going to start from the first one, atomic radius. The size of an atom is, of course, determined by where the valence shell electrons reside away from the nucleus, right? Okay, so we're going to use Coulomb's law to explain this. Again, the atom consists of the positively charged nucleus and then the negatively charged electrons. The thing is, there are multiple shells. Okay, so in the innermost shell, there are 2 electrons, and then starting from the second shell, there are you can fit in a maximum of 8 electrons. So let's say this is a model of 1s2 and then 2s2. So you have 2 electrons on the valence shell. Okay, then how the atom size is determined is by the attraction force between the valence shell electron and the nucleus. Okay, so which carries a positive charge. We know that the like charges repel and all like charges attract. Okay, so the positively charged nucleus and then the negatively charged valence electrons attract each other. And then the amount of attractive force can be calculated using the Coulomb's law. The force is equal to the constant, the Coulomb's constant K, multiplied by charge 1 multiplied by charge 2 divided by r squared. So r represents the distance between the electrons and then the nucleus. And then the Q1 represents the charge of the nucleus, and then the Q2 represents the charge of the electron. So let's say I'm going to compare the lithium and then the beryllium. So it carries the charge of +3. Then it has 2 electrons on the first shell, and then it has 1 electron on the second shell. So this is lithium. Okay, then what about beryllium? So beryllium actually has 1 more protons. So it has +4 as the charge of the nucleus, and then it has 2 electrons on the innermost shell, and then 2 electrons on the second shell. Okay, so this means that the Coulomb's force between the valence shell electrons and nucleus of lithium is smaller than the Coulomb's force experienced by the valence electrons and nucleus of the beryllium. Nucleus attract the electrons more toward the center, so beryllium will result in a smaller size. So attractive force between the nucleus and valence electrons increases across the period. When I say across the period, it always refers to left to the right. This means the radius decreases. So distance between valence electron and nucleus decreases across the period. What if I compare the lithium to the sodium? Okay, so lithium and sodium, both of them are in group 1. One is in the shell of n equals 2, one is in the shell of n equals 3. Okay, so obviously sodium has one more shell, which means the valence shell electrons will be further from the nucleus. So the reason why so of course the distance between the nucleus and an electron will increase when you go down the periodic table. The number of the shells increases down the periodic table, and thus valence electrons experiences less attractive force from nucleus. This can also be explained by the repulsive force in between the core electrons. So electrons on the outermost shells are called valence electrons, and all the other electrons inside are called core electrons. Okay, and then the more shell you have, the more core electrons you have, and then the repulsive force between core electrons increases, and this compensates for the attractive force between the valence electron and the nucleus. So it kind of diminishes that attractive force. And we call this electron shield. We call this increasing repulsive force between core electrons. We call this electron shield. This is a summary of the atomic radius. So from left to the right, across the periodic table, it gradually decreases, and then from top to the bottom, it gradually increases. Okay, the next will be the comparison of the atomic radius and ionic radius. There is no certain rule for this. So for some of the atom, their atomic radius is bigger. For some of the others, their ionic radius is bigger. Lithium or beryllium. So in general, for alkaline earth metal and then alkaline metal in group 1 and group 2, when they form an atom, they usually form cation because they're losing electron, which means their energy, the number of the shell is actually decreasing. So let's say for lithium, its valence shell electron is on n equals 2. When it loses one electron, it actually decreases to n equals 1. Okay, so it lost one whole shell. So its size will actually decrease a lot. And it's the same for like all the other alkaline metal and alkaline earth metal. So let's say for magnesium, when it loses 2 electrons, it also lost one shell. So its size will decrease by a huge amount. On the other hand, for some other atoms such like halogen or the atoms in group 6, when they form an ion, they usually gain electron and form anion. Let's say for chlorine, it's gonna gain an electron and be converted to chloride ion. Okay, then compared to its size, because of the extra electron, its size will actually get bigger. And it's the same for the oxygen. So oxygen gains 2 electrons to form O2 minus. So its size gets so much bigger. So you need to pay attention to if it's a cation or an anion, if it's losing an electron or gaining an electron. The second of the periodic table will be first ionization energy. Okay, so ionization energy is the amount of energy required to remove an electron. If I want to remove an electron from magnesium, then it will be magnesium converts into magnesium plus and an electron. Okay, so a lot of people think, oh, this is gaining an electron because you have plus electron, but that's not true. It means magnesium is going to split into 2 parts. One is the electron, and then one is the magnesium plus, the magnesium cation. Okay, and then it's going to take a certain amount of energy. Let's say you want to break something, then it always takes energy. It's not releasing energy. It doesn't happen like just naturally. You need to put in energy to make sure this like breaking process happens. So that's the same for an atom. If you want to remove an electron from an atom, then you need to put in energy, and it takes energy, and that amount of energy is called the ionization energy. And first ionization energy means when you remove the first electron from an atom. Okay, so you can keep removing removing electrons from magnesium. So from magnesium plus, you keep removing the electrons, so it becomes magnesium 2 plus. Then this is the second ionization energy. So we are going to deal with the first ionization energy first. Okay, so for the first ionization energy, it increases from left to the right, obviously. And then it decreases from top to the bottom. Okay, this is a general trend. And this is because when you go from left to the right, remember that atomic radius decreases. So because of the increasing effective nuclear charge, it's going to be more and more difficult for me to remove the valence electron. From left to the right, the nuclear charge increases from left to the right. So it gets harder to remove an electron. So it takes more energy. But when you go from top to the bottom, because the valence shell electron is further away from the nucleus, which means it doesn't experience that much attractive force. So it's much easier to remove that electron from the atom. There are couples of exceptions for first ionization energy. Okay, again, this is first ionization energy only. If you take a look at this diagram, you observe that from left to the right, the general trend is increasing, but from group 2 to group 3, there is a decrease. And then from group 5 to 6, there is another decrease. Across group 5 to 6, you observe this trend. And across group 2 to group 3, you also observe this trend of decrease. Okay, and why is it? Okay, so this is the first ionization energy of the elements in n equals 2 shell. Okay, from lithium to beryllium increases, but from group 2 to group 3 decrease, and then increase, decrease, increase. This trend holds true for all of the period. And this is because how electrons are filled in the p subshells. Let's try to draw the electron configuration of beryllium and the boron. Beryllium has electron configuration of 1s2, 2s2. If I try to draw the energy diagram, then it will be 1s up and down, and then 2s up and down. Okay, and for the boron, it has electron configuration of 1s2, 2s2, 2p1. So again, it will be 1s up and down, 2s up and down, and then for 2p, you are going to fill in only 1 electron in 3 orbitals. Okay, so now if you are trying to calculate ionization energy, you need to remove these electrons. we need to remove this electron from boron and this electron from the beryllium. Okay, so now the beryllium has fully filled 2s subshell, which means it's very, very stable. So if you want to break this stable state and remove that one electron to make it unstable, it's actually going to take a lot of energy. On the other hand, for the boron, because only one unpaired electron is in the whole 2p orbital, which makes it unstable. So if you want to knock off this electron and then make it into a stable state, then it's relatively easy. So we call this that beryllium has fully filled 2s subshell, while boron has only one unpaired electron in 2p subshell. So it is relatively easy to remove the single electron in 2p of boron and make it stable. Then what about from nitrogen to oxygen? This is a trend that you observe from group 5 to group 6. Again, let's try to draw the electron configuration of of nitrogen. Nitrogen is 1s2, 2s2, and then 2p3, while oxygen is 1s2, 2s2, 2p4. Okay, I'm going to draw the energy level diagram. For nitrogen, 1s up and down, 2s up and down, and then 2p, it is up, up, up. For the oxygen, it's 1s up and down, 2s up and down, and then 2p up, 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 down. Okay, so now when you're calculating again the first ionization energy, you are trying to remove the electron in the 2pz orbital of the nitrogen, and this one of the paired electron in 2ps orbital of the oxygen. Okay, so which one is easier? So even though like nitrogen doesn't have the fully filled orbital, it has a half-filled 2p orbital, which also makes it stable. Okay, so if you want to break this stable state and remove the electron, then it's going to be relatively difficult. On the other hand, for the oxygen, it has this extra electron here, even though it's paired, and usually the paired electrons are stable, but because the other two orbitals are not paired, so this is actually more unstable. If you want to knock off this electron and make it into a stable half-filled 2p subshell, it's actually preferred. So it's easier to remove this extra electron. So it is because nitrogen has half-filled 2p subshells. So it is relatively difficult to remove an electron from 2p subshell of the nitrogen. Next is electron affinity. So electron affinity and ionization energy is a pair of opposite terms. So ionization energy is the amount of energy required to remove an electron. Then electron affinity is the energy change that occur when an atom gains electron. So let's say fluorine gains an electron to form fluoride, then the amount of energy that is usually released is considered electron affinity. Then in this case, electron affinity will be a negative value. Okay, so from left to right, electron affinity increases. The last one will be electronegativity. So electronegativity is very similar to electron affinity, but it's actually different. So this is the tendency of an atom to attract electrons, especially the shared electrons. Okay. So electronegativity is used more often when it comes to the bondage between two atoms. Okay, so let's say two hydrogen atoms form a bond, okay? Then it means the two hydrogen atoms are actually sharing the electrons, okay? So this is the electron of the left hydrogen, this is the electron of the right hydrogen, and they are sharing two electrons with each other, okay? So for two hydrogen atoms, they have the same size, the same mass, and then they have the same electronegativity. They attract the electrons with the same force, with the same attraction. So the electrons will be equally shared. The electrons will be right in the center. But what if it's the hydrogen and fluorine, okay, or hydrogen and chlorine, okay? So chlorine has a much greater electronegativity, which means it's very, very strong. It can just pull the electrons toward itself. So when hydrogen and chlorine share electron, the chlorine will just pull the electrons toward itself. So hydrogen barely gets to share that shared electrons, even though it contributes one electron and to form the bond. Okay, then this means electrons are shared unequally. And this is because chlorine is more electronegative than hydrogen, which means chlorine is stronger when it comes to attracting the atoms, attracting the electrons when they form a bond. Okay, so if one atom is like too strong compared to the other atom, then eventually the electron will be just fully transferred to that atom, and then the other atom will just lose an electron. Okay, so we're gonna deep dive into electronegativity difference and the bonding in Unit 2. We're gonna learn different types of bonding, and then different types of chemical bonds actually is due to the difference in electronegativity. Okay, so this is a chart for the electronegativity of the elements, and you can tell that when you go from left to the right, the general trend is electronegativity increases. This is because when you go from left to the right across the period, the effective nuclear charge increases, so a stronger attraction towards the electrons. Okay, and from top to the bottom, it decreases. And of course, this is because the more shell it adds, the more shell it has, the weaker attractive force forms between the electrons and the nucleus. Okay, so let's say, for example, hydrogen and fluorine, they have electronegativity difference of 4 minus 2.1. So the electronegativity difference is 1.9. This is actually considered a very big difference in electronegativity, which means hydrogen is too weak and fluorine is too strong. So fluorine will actually just gain that electron away from the proton, from the hydrogen, and hydrogen will be actually left with no electrons left. Okay, but when we compare the hydrogen and chlorine, even though the difference is still big, 3.0 minus 2.1, but chlorine is not as strong as fluorine, so they are still kind of sharing the electron. But this is still unequal sharing of the electron. The electrons are dragged more toward the chlorine. In terms of the atomic structure, explain why the atomic radius of potassium is larger than that of sodium. Okay, so on this periodic table, potassium is on the energy level of n equals 4, and then the sodium is on energy level of n equals 3. Okay, so potassium is larger because potassium has more energy shells, or more energy levels, or more shells. So potassium experiences more shielding of the core electrons, which means the valence electrons of the potassium experiences less attractive force towards the nucleus. Okay, B, in terms of the atomic structure, explain why the first ionization energy of the potassium is less than that of calcium. Okay, so when we compare the potassium and calcium, they're on the same energy level, but potassium is alkaline metal and calcium is alkaline earth metal. So, which means calcium has one more protons compared to potassium. So, potassium has less effective nuclear charge than the calcium. So, it is easier to remove the valence electron from potassium compared to calcium.